Assalamu alaikum and hi everyone. So today we are from group for section 4. We will present about our group project, a power system simulation for overcurrent protection grading purpose. Alright, before we go further, let me introduce our group member first. My name is Muhammad Syaifuddin and we have IZZAT IMRAN, Wan HAZIQ, TAUFIQ and HENG. Alright, let's go to the introduction part first. Overcurrent protection help prevent damage by cutting off excessive current from fault like a short circuit or overload. In this project, we will simulate a basic power system to see how current behaves under the three conditions. First, a maximum load. Second, a minimum fault current. And third, a maximum fault current. The goal is to understand how these conditions affect the system and how to set the overcurrent protection relay to keep everything safe and reliable. Alright, for this project, we have three objectives. Our first objective is to develop and simulate a power system model based on a credible reference. Our second objective is to analyze a current magnitude under a various load and fault conditions. First, a maximum load current. Second, minimum fault current. And third, a maximum fault current. And our third objective is to prepare data for overcurrent relay protection studies to ensure accurate protection setting for system safety and reliability. Alright, this is our system one line diagram. This diagram represents the simplified power system model, including a key components such as a generation source, a transformer, power line, and a protection zone. The system is designed to simulate a different loading and a fault scenario for our overcurrent protection analysis.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad IMRAN ZUKIFLI, number matrix AE220050. So for my part, I will explaining about the simulation of the power system protections of our assignments. So for the requirement for our assignment, which is the guideline, so we need to choose a power system models that include two generation source, three transformers, and 4 to 5 lines. So we follow the guideline and we follow the our reference circuits. And this is the circuit that we got. We have two power generation source, four transformers, and six transmission lines. So for the maximum load analysis, we can remove the fault first and we can write. So after the runnings, we can see the scope. So here's our result for the voltage. It's approximately 6,000 because we set the transformer here to 33 to 11s. So when the voltage reach to line to neutrals, so it will divide by power of 3, so it will become 6,300 or something. So for the currents, here we get approximately 280, and then that's for the fault analysis. The bottom ones is also the same, 6,000, and for the current one also the same for the bottom one. Oh no, it's bugging. And then we can run our minimum fault analysis. So connect each phase for the phase A, B, and C. And we want to do the minimum fault analysis. So typically a remote line to ground fault at far ends. So for the fault, we need to set whether choose any of the phase. You can choose phase A, phase B, or phase C, and connect it, pair it with the ground. So you can choose phase A, phase B, or phase C, but with the grounds. So from here, I choose phase C and the grounds. and then we can run. Then after we run, we can see that for the phase C, interruption occurs for 0.5 seconds here because I set the uh, fault is set at 6 to 6.5. So the fault occur only at 6. So this is the beginning of the interruptions. And this is the end of the fault. This is the end of the fault. This is for phase C, minimum fault. So this is for the voltage. If you see for the currents, it's also the same. It's become interrupted for the starting and also the so for the other ends. And after that, we can run for the maximum fault analysis, which is a three-phase fault near the source end of the line. So we need to change this. We need to choose all of the phase A, phase B, and phase C, but we don't need the ground parts. So we click OK, and we can run. So after that, we can see that for the all of the phase, it occurs the fault. So for the fault A, B, and C, it's happening the fault, and it occurs at the same times, which is the 6 to 6.5 seconds. This is the beginnings of this is the beginning of the fault, and this is the other ends of the fault. So for the current also is the same. This is the ends, and this is the beginning of the fault. And I think that's all for me. I've done the simulations on how to generate the data we get from the maximum load analysis, minimum fault, and maximum fault. That's all from me. Thank you.
So for our first result and discussion is our maximum load condition. So here you can see the two graphs that we get after we do the MATLAB simulation for our project. So the maximum load current here will be the top part, and you can see that for each of the graph, you can see there's a phase difference between the graphs. And then the bottom here is the maximum load voltage. So the current values during the simulation, the current during the maximum load state within the expectation, and then it ensures that there is no overloading of the equipment. Next is our voltage behavior. Our voltage remain stable, confirming that the system can handle peak demand without any issue. And as for the impact of the protection, this result shows that it will help us to set proper overcurrent protection relays so that we can avoid equipment damage during high load.
Alright, so we move to the minimum fault current. So about the current value, the current during maximum load stayed within expected limits, ensuring no overloading of equipment. For the voltage behavior, the voltage remains stable, confirming the system could handle peak demand without issues. And the last one, impact on protection. The result will help set proper overcurrent protection relay settings to avoid equipment during high load. So as we can see, this is the left side is for the voltage for minimum fault current, and the right side is current for the minimum fault
So the
current.
next part is maximum fault current. This is our result. So the first fault current, the three-phase fault at the source and result in high fault current, showing the severity of fault near the power source, as shown in the figure. For the system response, the system quickly respond with a significant current spike. which could potentially damage equipment without proper protection. So for the protection inside, this result emphasizes the importance of setting overcurrent. Protection relays too active before high fault currents and cause harm to the system.
Alright, last but not least, in conclusion, this simulation emphasized the importance of accurate overcurrent protection setting for maintaining a system stability. Under the maximum load, the system managed the peak load effectively. We also successfully simulate both minimum and maximum fault current, showing how the system reacts to the different fault severities. This key takeaway is that the proper relay settings are essential to prevent a damage and ensure timely activations of a protection zone. For future work, we could explore refining a protection scheme to handle more complex fault scenario and improve overall system resilience. I think that's all from our group. Thank you.